So this is our second video on kinetics, and here I'm going to talk about the integrated rate laws. So we're going to go through the various cases that we can have here: zero order, first order, and second order, right? So for a zero order reaction, if you remember from the previous video, if you look at the rate law, the rate is going to be equal to some constant K times the concentrations of the reactants raised to their various powers. Now, if one of those powers is zero, anything raised to zero is the number itself, which means that term would drop out of the rate law. Okay, so this is the only case where a reaction rate does not depend on concentration, and the reaction goes at a constant rate. So for example, if you have 0 minutes, in other words, that's when we start the reaction, you have 1 mole. Suppose 1 minute into the reaction, you have 0.75 moles. 2 minutes, you have 0.5 moles. How many would you have after 3 minutes? Well, something is a straight line when you have constant intervals in both variables. In other words, this is a constant interval, and this is a constant interval. From 1 to 0.75 is the same change as from 0.75 to 2.5. So after 3 minutes, you'd have 0.25 moles, right? If you graphed this, concentration versus time, right, it would be a straight line. So a plot of reactant concentration versus time gives you a straight line. Okay? Now, what if you have a first order reaction? Well, now the rate is not constant. Okay, the rate depends upon the concentration in the first order. The concentration is constantly dropping, so the rate or the concentration follows rather logarithmic decay. All right, so that's going to be this equation. Okay, so the natural log of the ratio of the concentrations, initial concentration divided by the concentration at time t is equal to kT. Okay, so if you have a first order reaction, a plot of concentration versus time gives a logarithmic decay, right? So if you plot concentration versus time, okay, it would wind up looking something like that. It would follow a logarithmic decay. Now a plot of natural log of the concentration versus time gives a straight line. So if we plotted natural log of the concentration versus time, then we would have a straight line. So concentration versus time is a logarithmic decay, and the natural log of the concentration versus time gives us our straight line. Okay. Now, what if you have a second order reaction? Well, again, the reaction rate is not constant, but it's going to be proportional to, now it's going to be proportional to 1 over the concentration. Okay. And second order kinetics is going to follow this equation, that 1 over the concentration at time t minus 1 over the initial concentration is equal to kT. So now, if your reaction is following second order kinetics, a plot of 1 over concentration versus time gives a straight line. So if we plot 1 over the concentration versus time, okay, now we'll have the straight line. Okay, and that's second order kinetics. So these two equations that you need to know. One is this is for first order kinetics, and this is for second order kinetics. Let's work an example. Okay, so example of a first order kinetics problem. So sucrose hydrolyzes into fructose and glucose in water. Okay, so it's a first order reaction, and the rate is proportional to the concentration of sucrose to the first power. You don't see a 1 there, but the 1 is implied. And K is 6.2 times 10 to the minus 5th per second. And let's say the initial concentration is 0.4 molar. Okay, so the first thing we want to know is this. What will be the sucrose concentration after 2 hours? Okay, so we know that the natural log of the ratio of our concentration, we'll put brackets around that whole thing just so you'd be sure. It's the natural log of the ratio of the two is equal to KT. Now, let's see, where did I get 7,200 seconds, right? We got to be consistent with units. The rate constant is so many per second, and I gave you the time in hours, right? So 2 hours is 7,200 seconds. So the natural log of the ratio, we know what the initial concentration was, 0.4, okay? Divided by concentration at time t is equal to 0.4464. The 0.4464 is 6.2 to the minus 5th times 7,200. Okay, so how do we solve this? We've had to solve problems like this before. You got to get rid of the natural log. You can't just say 0.4 over the time, or concentration at time t is equal to 0.4464. You have to get rid of the natural log. And remember, you can do anything algebraically, we can do anything we want to an equation as long as we do the same thing to both sides. So we can add something to both sides, we can subtract, we can multiply, we can divide, we can take the log, or we can take the inverse log of both sides. Okay, so the inverse natural log of the natural log is the number itself. So by taking the inverse natural log of both sides, we get rid of the natural log. So what we're really saying then is 0.4 over concentration at time t is the inverse natural log of 0.4464. All right, so we would take, see if I can show this here. So we'll take 0.4464, okay, and we're going to take the second function, natural log, which is the same thing as saying, notice it also says e to the power, which is the same thing. So we're going to do a second function, natural log, and you get the 1.56, all right? So that's how I got the 1.56. So from here, it's just simple algebra. All right, so 0.40 over the concentration at time t is equal to 1.56. Concentration at time t comes out to be 0.26 molar. Okay? Now let's work the second part of this problem. How many minutes will it take for the sucrose concentration to drop to 0.3? Now we're still assuming that we start at 0.4. So how many minutes will it take for our concentration to go from 0.4 to 0.3? This is perhaps a little bit easier to solve, so we don't have to take the inverse natural log anyway. So the natural log of the ratio of the concentrations, 0.4 over 0.3 is equal to KT. T is what we're solving for, right? So 0.4 over 0.3, you take the natural log of that, and you get 0.28768, right? So we take 0.4 divided by 0.3, it's 1.33, and we take the natural log of that, that's 0.28768. That's equal to KT. 6.2 to the minus fifth times the time, and the time comes out to be, because our rate constant was in units of per second, our time comes out to be in seconds. That is 4602 seconds, or 76 minutes. Okay. Now let's work a second order kinetics problem. Okay. So the reaction of NaCl, nitrosyl chloride, I believe, decomposes into nitrogen oxide and half a mole of chlorine gas. Okay, so it's a second order reaction. So our rate, that means then that our rate is going to be equal to some constant K times the concentration of nitrosyl chloride squared. Okay, and K is 0.020 liters per mole per second. Okay, so first thing we want to know here is okay, how many minutes will it take for the concentration to drop from 0.040 to 0.010. Okay, so we take 1 over 0.010 minus 1 over 0.040. That's equal to K times T. Right, so 1 over 0.01 is 100, 1 over 0.04 is 25, 100 minus 25 is 75. And notice moles per liter became liters per mole, because, right, we were taking 1 over, is equal to KT. Okay. And you divide, and T comes out to be 3750 seconds, or 62.5 minutes. Okay. So let's go on to half-life. So what is half-life? It's the time required for half of a given amount of substance or amount of reactant to disappear. All right, so as before, let's talk about the first order kinetics first, second order. We'll go through them one by one. So first of all, first order kinetics follows this equation, that the natural log, and one more time, it's the whole ratio. So it's the natural log of the ratio of initial concentration divided by concentration at time t is equal to KT. Okay, so let's derive this. So at time t, we're going to plug in the condition for half-life. One more time, it's the time required for half of your amount of time to disappear. So right, this is our integrated rate law for first order kinetics. So we're going to plug in the criteria that the concentration at time t is half the initial. Right, so concentration at time t is equal to 1/2 the initial. So now we have the natural log of the ratio of the concentration, initial concentration, divided by 1/2 the initial concentration, right? And so the concentrations will cancel, and what we're taking the natural log of is 1 over 1/2, which is 2. Okay, so this comes down to ln2 is equal to KT. Now, this is very important. I don't see the concentration in there anywhere. The concentration canceled out. Okay, so for first order kinetics, the half-life is independent of reactant concentration. It doesn't matter how much you start with. at the end of the first half-life period, at the end of your first half-life period, half of it will be gone. So if you start with a mole, at the end of the first half-life, you'll have half a mole. If you started with 100 moles at the end of the first half-life, you would have 50, because the reaction goes faster at the higher concentration. Okay, so let's say, for example, let's say we have some material. We start with 100% of our material. Okay, whatever we're reacting. And at the end of the first half-life period, let's say, we have 50% remaining. Okay, and then we have 50%. What's half of 50%? Half of 50% is 25, so we have 25% remaining. And what's half of 25 is 12.5. So that comes down to 12.5%. Each of these would take the same time. So it takes the same time to drop from 100% to 50% as it does from 50 to 25, as it does from 25 to 12.5, because the reaction is slowing down. But each of these is half what's before. And one more time, it's the same time period. So this would go from here to here, would take the same time as from here to here, as from here to here. It's the time required for half of your material to disappear. 50% is half of 100, 25 is half of 50, 12.5 is half of 25. Okay? The half-life does not depend on concentration. Okay? Very, very important concept. Okay? So what about second order kinetics? Let's do the same thing. Let's derive it. So this was our integrated rate law for second order kinetics. Alright, so 1 over the concentration at time t minus 1 over initial is equal to kT. So we'll plug in the criteria that concentration at time t is equal to 1/2 the initial concentration. So 1 over 1/2 the initial concentration minus 1 over the initial concentration is equal to kT, or 2 over the initial 1 over 1/2 is 2, right? So 2 over the concentration minus 1 over is equal to kT. And so this comes out to 1 over the initial concentration is equal to kT, or T is 1 over the rate constant times the concentration. So the half-life, the concentration is on the bottom. Okay? So half-life is inversely related to the concentration. What does inversely mean? As one number gets bigger, the other one gets smaller. Because the concentration is on the bottom. If we make the concentration bigger, the half-life is actually going to be smaller, because the reaction is going to happen faster at the higher concentration. Okay? So let's go back to first order now, and let's work a problem, and let's go back to this problem that we looked at previously. Okay, so we're looking at the sucrose, at the decomposition of the sucrose and the fructose and glucose. We said that it's a first order reaction, and it has a rate constant of the rate is some constant K times concentration of sucrose to the first power. We said the rate constant is 6.2 to the minus fifth per second. Okay, so first thing we want to do is find the half-life, right? So T1/2 half-life is ln2 over K, or ln2 is equal to kT. Rearrange that to solve it for t. So t is ln2 over k, and the natural log of 2, you can figure that out on your calculator. you take 2, okay, we take 2 and, no, I'm sorry, not inverse log, natural log is natural log. If we take 2 and the natural log of 2 is 0.693, right? So t is 0.6, t1/2 is ln2 over k, 0.693 over 6.2 to the minus fifth. That's what? 11,177 seconds, which comes out to be 186 minutes. Okay. Now, let's ask this question. How many minutes would it take for 75% of the sucrose to react? Now, there's an easy answer to this and a harder answer to this. Let's do it the easy way first. If you understand half-lives, there's an easy way to answer this question. Remember, as I said this on a previous slide, after the first half-life period, you have 50% reacted. Okay, so during the first half-life period, 50% of your original material reacts. Okay, after the second half-life, we've had 50% of the 50% reacted. So the 50% becomes 50% reacted, so we're now 75% reacted. And after the third half-life, then 50% of the remaining 25% reacts, so now we're up to 87.5% reacted. Right, so there's an easy answer to this question. To get to 75% reacted, that's 2 half-life periods. So basically 2 times 186 or 372 minutes. Now, you could also work this out mathematically and you would get the same answer. Okay? Okay, so if we're 75% reacted, that means we have 25% remaining. So the amount that we have at time t will be 25%. So natural log of 1 over 0.25 is equal to 6.2 to the minus fifth times the time in seconds, right? So what? You guys should know what's 1 over 1.25. That's 4, right? If we would take 4, natural log of 4 is 1.38, and we divide that by the 6.2 to the minus fifth. That was their rate constant, right? And that's what you get. 359 seconds, which you divide it by 60 comes out to be 372 minutes. So if the quantity that you're seeking falls upon one of these boundaries, 50% reacted, 75% reacted, 87.5% reacted, you can do it this way. If it doesn't fall on one of those boundaries, then you'd have to work it out the long way. Let's say we wanted 40% time for 40% to react, then you'd have to do it this way and work it out mathematically. All right, we'll stop here.